Hello, the topic of this video is ultrasound imaging. Ultrasound has many applications in radiation therapy. For example, it's being used and has been used to position the prostate at the time of external beam radiation therapy, where you'll take an ultrasound image and that's coupled to the linear accelerator treatment, and you can image and treat. It's also been used for many years to guide implant procedures. A classic example being prostate brachytherapy, where you have a probe that you can visualize the prostate, and then you insert seeds as you're visualizing it with the ultrasound. So it's important to understand this modality at some level, and so hopefully this video will provide you with some basics. Here we go. Let me just start by showing an image. This is a prostate scan for an implant, and the probe is actually down here in the rectum. It's the circle at the bottom, and then you're visualizing the prostate. It's outlined here in green. And the grid is for inserting seeds. Seeds are actually inserted with this stepper mechanism to index exactly how far in you want. And the probe sits in this holder, and then the seeds are put in, and here's a picture of where the seeds go in the end and the dose distribution. So let's talk about how you get there, how ultrasound works. So ultrasound can be described as a pressure wave. So I'm going to try to draw this schematically. What I'm drawing here is pressure. The closer the lines are together, the higher pressure is in this material. This could be air or tissue or water or something. And so it's sort of low pressure, high pressure regions, pressure wave. Incidentally, this dates back to the work that's done in World War II with sonar in water, and then that got translated over into medicine like so many applications. And especially when computers started to come around, you could start to generate images. So that's where some of the history is. Now this pressure wave propagates through the material at some speed. I'm going to call that V. So you should know the frequency of ultrasound. It operates between 3 and 10 megahertz, and we'll see in a minute that speed and frequency are related. Let's write down some of the speeds. So in air, the speed of these waves would be 330 meters per second. In water, it's substantially faster, 1,480 meters per second. You'll see that the denser medium, the wave travels faster because there's a tighter coupling between the atoms in the material. Soft tissue, it's a little faster yet, 1,540 meters per second. That's a number that's good to know. Okay, very good. You've got pressure waves moving through a medium, but how do you form an image out of that? So let me walk through that with an example. So let's start at the surface of the patient here, and let's say I want to image something down here, this plane. I'll talk about forming the image in a minute, but for now I just want to know where that plane is. So I put a probe on the surface of the patient, the ultrasound probe, and it sends a pulse down, ultrasound pulse, at some speed V. Now that pulse reflects off this object I'm trying to image, and it comes back up, and then the probe reads it. So that reflection is the key part here. So let's say it's fat above and muscle below, and I want to see where that interface is. So that the reflection is makes that possible. So you can know the distance down. The distance is just the speed times the time it took for the pulse to come back to the probe, divided by 2, and the 2 is because it has to go down and then back up. So the reflection off this interface is due to what we would say a mismatch in the impedance, which is given the symbol Z. Impedance, it can be found by this. It's just the speed times the density in the material. So a larger mismatch in the impedance leads to more reflectivity. That's the basic idea. So you can imagine fat and muscle, there's a reflection. Fat and bone, there would be a huge reflection, right? In fact, so much that you get artifacts. So let's go back to these waves. The pressure waves have some wavelength, lambda, just like waves that we've seen before. One key thing is that in order to image, the size of the object you're imaging has to be less than the wavelength of the ultrasound wave. If it's not, then you get reflections off these small objects that come back and make kind of speckles. And that's one of the reasons why ultrasound images are so speckly. Now we can write down the formulas for speed and wavelength. So speed is equal to wavelength times frequency. You'll remember that equation. It's the same as for electromagnetic radiation. You can invert that and say that the wavelength is the speed divided by the frequency. So let's do an example. The frequencies are, by the way, are 3 to 10 hertz, right? Megahertz. So the example, let's do 5 megahertz ultrasound. What is the wavelength of that? So use your formula. Wavelength is speed. Let's do it in soft tissue. 1,540 meters per second divided by the frequency in hertz, which is 1/seconds. And that comes out to be 0.31 millimeters. So you can see it's a relatively small wavelength capable of imaging pretty small objects. Let's go back to this picture of the wave going in. You have this ultrasound wave propagating down into tissue, and as it does, it's attenuated, so the pressure differences become less and less the deeper you go. I can write an equation for that. You can imagine what it is. You start with some pressure at the top. It's e to the minus alpha d, okay? And actually, alpha depends on frequency, so we usually write this alpha of f times d. And alpha of f, it's approximately proportional to frequency. So it goes up as frequency goes up linearly. So that means that at higher frequency, so alpha f is bigger, and there's more attenuation of the ultrasound beam. So that's a key concept in ultrasound. Higher frequency, more attenuation. Or alternatively, lower frequency, you can go deeper. Now strictly, this only really applies in the far field limit, so kind of far away from the face of the probe, but it's a good concept to have. All right, so I still have not told you how we make an ultrasound image, but we have all the concepts. Let me see if I can walk through this. So let's say you want to image 2 objects here underneath the probe at different depths. Okay, so what that would involve is resolving the fact that the reflections off the 2 of these come back at different times to the probe. If you can do that, then you can image it. Yeah. So what you do is you send out a pulse from the ultrasound probe. This is called the spatial pulse length. That's the length of it. It's typically, let's say, 3 cycles of ultrasound, and then it shuts off, and you wait for that to go down and then reflect back. So that spatial pulse length propagates down. It reaches this first object and reflects back and starts going backwards, but then part of it is still going down, and it's going to reflect off the second object, and then that's going to reflect back, and now you've got the 2 pulses going back up towards the probe. Now I think that what you can convince yourself of is that if these objects are closer together than half the spatial pulse length, then you can't resolve them. If they're farther apart, you can resolve them. So that controls the resolution and the imaging. So when you have a higher radio frequency, this spatial pulse length becomes smaller, and you're able to resolve features that are closer together. Okay, so that's the basics of this. I still haven't told you how we make an ultrasound image. Maybe I never will. No, let me try. You can just imagine extending what we just talked about. Imagine taking many rays out of the probe in different directions. And if you could do that, then you could eventually build up a picture, especially if you had a computer to help you do it, which is what came into use in the 70s and 80s. And that's what you do. And so there are these little piezoelectric pressure objects, transducers they're called, in the probe, many of them, and you can electronically control them, scan back and forth, and get these different lines that will give you an image. And then that's the one dimension. And the other dimension, you can move the probe back and forth, or sometimes you can do it that electronically as well. Okay, so maybe I told you how an ultrasound image is made. So those are the basics of ultrasound imaging. Hopefully this is helpful. Here are a list of further reading materials if you want to dig deeper. And with that, we're going to end the imaging section. And hopefully it was very brief, but hopefully it gives you an underpinning for learning more. Thank you.